Right, so my name is Ingo Luetkebohle. I'm with Bosch Corporate Research. Similar to what the ABB guy said earlier, we're sort of the middle ground between university research and the industrialization side. And today I would like to talk a little bit about our activities towards embedded ROS-II. And this is partially supported by the European grant, and I will also be mentioning a few of the partners later on. Right. Before we start, I would like to give you a little quiz. And does anybody know what this is? So the hint is it's from a very important ROS robot. That's about what I expected, seriously. So what this is it's the arm of the PR2 and the insides of that arm. And I'm bringing this up because I think it's one of the areas that we take for granted. It's there, it's the hardware, it's the electronics, it's the microcontrollers. But we don't, as a community, or at least a large part of the community, doesn't look at this very often anymore. And I would like to convince you with this talk that we should do this as well. Not at the expense of other stuff, but as well. So, and this is actually already a goal of that underpins the ROS-II development. This is taken from the ROS-II design wiki in the stories page. And it says, in the future it could be possible to implement the ROS protocol, whatever that means, directly on the device's embedded system. Well, if we look at why we want to do that, and the reason for that, why we want to do that is because robots are networks of devices. And I put up here two examples. One of them on the left is early robotics, now Ecotronic Robotics, early drone. And as you can see, there's a general purpose computer on there which runs Linux. And there's a couple of microcontrollers, ARM Cortex R4, M4, and M3. And on the in the middle, there's the undercarriage of the Bosch Indigo autonomous lawnmower. And I just placed the boxes roughly over where the microcontrollers are in the physical system. And as you see, there's 4 bigger microcontrollers, a couple of sensors, each which also have microcontrollers on board and that. So, and what we typically see is that we have this separated system. We have on the one side a Linux-based, ROS-based system running on a microprocessor, and then we have smaller microcontrollers running some kind of firmware on a microcontroller and directly attached to the eventual hardware, like a sensor or an actor. And these are connected by a serial bus. All of this is what is usually called embedded. But what I would like to focus today is the lower part. Because the upper part, putting Linux into embedded systems, that's fairly well understood. Still work to be done, sure, but you know, at least that's already in scope. But the lower part, that's something where we typically have just taken what's out there and written a driver. So, the question you might have when coming to this is why should we do this, right? You know, ROS and Linux is really a powerful combination. There's excellent libraries available. There's a unified developer ecosystem. I can install Linux on just about any of these ARM devices, x68 devices. Once they have a certain level, certain number, size of RAM, I can install Linux on it. And it's very convenient, right? Almost everybody has a Linux-based system or a system that could be running Linux on his desk. But there's a couple of things. One is what I just mentioned before, it's the hardware access. If you have a Linux system, even if it's a single board computer like a Raspberry Pi, the hardware is not directly on it. You always have some kind of connection, like a bus connection, a serial connection to the actual hardware. Then Victor had made a great show today of the various benchmarks they did with getting Linux to be really hard real time. But I can say, if you want to go even lower latency, Linux at some point reaches its limits. You don't need that for everything, right? It's not necessary everywhere. But if you want to go lower, it's difficult. And I will give some numbers later on what I mean by lower. The third is power saving. Linux has a decent power saving support, I would say, but I will again give some numbers later of how microcontrollers in these low-level embedded devices are way lower. And the third is safety. The fourth, Linux and safety, problematic topic. And now we'll go into each of these in detail. So, the thing with hardware access in Linux is you're always talking to some piece of firmware over Comlink. And you know, it usually doesn't do what you want. It does maybe sort of halfway get you there, but mostly not always. And there's latency, the communication latency. And then we implement drivers. You know, there's bunch of serial protocols, field buses, you know, standards of field buses and the protocols on top of them, really it's all over the place. And then when you look at the data sheets for the devices, lots of important stuff is not in there. How fast are they running? What's the latency? What's the control delay, control dead time, all that stuff. And state management, we don't even want to get in there. So my message, that's actually the message that I would like to get across today, is that we need to get into the firmware as well with an open source approach. That's what I believe in. That's what I would like to convince you of. So, and if we now look at the microcontroller in contrast to that, so the very definition of a microcontroller is a chip that contains both a processor and peripherals. And these peripherals could be analog digital converters, they could be quadrature decoders, what you need to interpret, you know, the encoders on your wheels, PWM generators, digital IOs, but also then a lot of buses. And the thing with these buses, then you could say, hey, this guy just said, you know, with Linux we all have these buses and we don't want that because it's latency and there's effort. Well, on the microcontroller, the bus is embedded and integrated at a much lower level. Typically, you just have a register where you can put some data on and it will be sent over the wire, or you can read from a register and you get what is sent over the wire. So, and the latency is completely different. But there's a problem also. I won't shy away from that. Well, that's a problem and a benefit. The benefit is so there's diversity in this. There's a lot of different microcontrollers with lots of different peripherals integrated. That's on the one hand cool, because it allows you to get one that's very specific for your application, and where a lot of the integration effort, which we all know is a pain in the ass, is already being done. On the other hand, we have to somehow cope with all that diversity. But next topic, real-time on Linux. So the Linux scaler has a real-time class, and you know, on a high-end PC, which is not what we are typically using in a robot, it can get down to like 5 microsecond task activation time. But there, you know, kernel processes can stall it, outliers up to tens of milliseconds, and so on. There's a preempt.t patch, solves some of that. There's always problems with other patches, proprietary drivers, and so on. And I have to say, this is after a decade of work on this. So just to give you an idea, well, this is useful. So on the right-hand side, task activation time without real-time priority. On the left-hand side, with real-time priority. So that's great. That's microseconds there. That gets us from 50 to 60 microseconds to below 10. That's cool. But there's outliers. That's without the preempt.t patch. You get outliers up to millisecond range. And so in that case, it's not reliable. So that's why you need the preempt.t patch, but even with that, what you get is deterministic on the left-hand side, but you don't get lower than that. And just to give you a small comparison, the NXP guys recently did a comparison of Zephyr and Linux. And this is just one particular piece of comparison, and I encourage you to read the whole thing. But what you should see is the context switch time, to switch between two threads. And this is in cycles on almost the same processor. So what you see is, well, it's a factor of 30. And this is basically the same story for all of the concurrency-related primitives in real-time operating systems. We see at least an order of magnitude, sometimes two, the real-time system being more responsive. Just saying, if you need that, that's the way to go. Power saving. Well, we all know battery-powered devices. We want to use as little battery as possible. On UAVs, the same. But also something which is not so well-known, but is a big issue, is standby operation. In the European Union, there's legislation that devices must not use more than one watch when they're in standby. And this can actually be difficult to achieve if you don't do power saving right. So, as I said, Linux has some decent power saving. These are a few numbers from, so the top are the Linux devices, the Raspberry Pi A and the Raspberry Pi 3. And as you can see, the idle use is around 150 milliamps. Operational use on the Raspberry Pi I is almost the same, 180 milliamps. And on the Raspberry Pi 3, it gets up to 800. So that's already fairly close. At 5 volts, it's already over the limit of what you could do in standby mode, right? And what you see here is that when we have microcontrollers, there's power-saving microcontrollers, which idle is 3 milliamps, and operational is 10 milliamps. And then even if you go to a more powerful class of microcontrollers, in operation, they use less current than what we would need to just idle a Linux-based system. And this gave a few sources here where I got those numbers from, and a couple of those are from the Opera project, internal measurements. Right. And the fourth issue, and actually, in my opinion, that's probably the most important part, really, safety. At the moment, what we typically see is there's a ROS-based system, and then there's a safety system underneath. And that's always a pain when going also into production. And there's always this interface, it's always an issue. And so people have been working on trying to get Linux safety certified for a while. So this is a slide I took from Carsten Emnes' talk at the Embedded World, 2011, 7 years ago, 7.5. And basically what he said at the time, real-time Linux took off around 2001. And then, here's where we basically need safety-critical Linux. So 2011 is what they started. They have a project, SIL2 Linux, targets safety integrity level 2, and the first thing it does is strips most of Linux, because Linux is just too big. And most notably, it strips a lot of drivers, because drivers are particularly problematic. But of course, drivers are also what we need when we want to access hardware. And this has been going on for years, and they recently said, I've wrote here, not clear what the outcome is. They recently read, they think they are being close in the sense that if you have a system where Linux is inside, you could get the system safety certified. That's a step, but well. And then I would like to point out the highest SIL level is 4. So maybe you don't need 4 all the time, but SIL 3 is pretty useful. So they don't even try that. And then for microprocessors is also having safety certified hardware. If you look at microcontrollers, you can get safety certified microcontrollers up to ASIL-D for €5 a piece, right? But try that with microprocessors running Linux. It's a whole different story. So, what's the answer? Well, the answer is basically that we're saying we want to use real-time operating systems. First thing is, well, they're optimized for real-time performance, but that's a prerequisite for safety. So there's also many safety-oriented real-time operating systems out there. And that's really the idea there. If we can, all of these issues that I just pointed out are mostly Linux issues, difficult to solve in the Linux space, but with real-time operating systems, we have a much better chance at addressing these. And in Opera, that's a project that I will be talking about next. The default system we're using is called NATEX. Its logo is on top here. It has a POSIX-style API, so that's actually pretty easy to port stuff to, which goes the same basic low-level API as Linux. And, well, there's other interesting choices. Riot OS, some people have even already tried, or ROS-2 on Riot. Free RTOS is a fairly popular choice. And I would just like to point you to Zephyr here. It's not what we are using in Opera right now, but it's going to be safety certified. And that's going to be the first open source safety certified RTOS out there. That's really novel. None of the other, I said you can get safety certified RTOSs, those are not open source in general. But Zephyr will be. Right. Actually, this is again a problem. We have so many to choose from. Which one do we use? They all have incompatible APIs. Not all of them are POSIX. Well, but still. And then we have the hardware diversity. I already got into that. Something unifying would go a long way, right? This would address not just our needs, it would also appeal to the current users of these microcontrollers and RTOSs. Something like ROS. That's at least our hope, right? That we could present something which doesn't not just benefits our community, but also benefits the deeply embedded community. And to that end, together with PIAP, Fireware, Aprosima, and Acutonic Robotics, we made a proposal for a European project called OFERA. Well, originally called MicroROS, but now called OFERA. And it got 15 of 15 points. Reviewers did really like it. And the basic idea is that we're going to take RCL, RMW from ROS, put it onto an RTOS, maybe with some abstractions to address multiple RTOSs. And then we are putting on some microcontroller-suitable middleware. And that's basically the approach that we're taking, and which I will now explain in a little bit more detail. Still have 10 minutes, I think. Okay, so we're targeting devices such as this. We're starting at 32 kilobytes of RAM. Typical device would be 100 kilobytes of RAM. Those are our two benchmark hardware pieces. Reason for 32 kilobytes is that we currently think that going below that would require a different architecture. And there's two reference boards. Right, so just skipping on that, then DDS is also going to need work. So that's the ROS's default middleware, but as is well known, people have tried putting DDS on microcontrollers, and the first thing they had to do was add additional RAM, and well, it's not going anywhere. So, and also DDS is problematic from a different point of view, because it assumes that devices are always connected. And as you may remember, one of our use cases was using battery-powered sensors, which may be in the environments, not getting updated for a long time, and then that doesn't work as well. So the OMG, with the participation of Aprosima, has worked on a new OMG standard for just this use case. They call it DDS XRCE for extremely resource-constrained devices. And the difference it does is what you see here on the image, it has a client-server approach. The embedded device is a client, and there's a server running on a more powerful computer. But the good thing is, because we've done that before, the serialization format is the same as with DDS. That's really the difference to what we had before, because you can just take a message from the client and put it on the wire, and the other way around. Cuts down on latency. Aprosima has done an implementation of an RMW layer for that. It's called RMUW Micro XRCE DDS, and that's the URL there where you can get it. Then for the client library, the approach now is use standard RMW, standard RCL. For TF, scheduling, and modes, we want to do specialized support to get really to what the embedded device need. And as was already mentioned, time synchronization is really important to get sensors synchronized, various devices synchronized. We also want to integrate that. As I mentioned before, we discussed the ROS-I-like approach. I personally quite liked it, but it would have been a lot of work, and so we're not going to pursue that at this time. And the idea is we provide a prototype implementation, and we have now founded a ROS2 embedded interest group that was done at this ROSCon in Madrid. And the first thing we did in that work is we did a pull request on the ROS2 embedded page. I encourage everybody to look at it. There's been quite a debate going on already, particularly on this, are we going to reuse RCL or not, and so on. But anyway, all input is welcome. Right. And that already sort of concludes my presentation. I will just give you a bit of information now. This is where we are developing. It's all on GitHub. And that's the OFERA website as well. This is again the pull request. After the merge, it will be at that URL. And we hope to get an initial merge done soon, and then we continue working on it to improve it. And, well, the last thing I would like to say, because now I've been talking about the European project of FERA and what it does and what its work package structure is, which might be a little bit boring. But this is not primarily about developing new stuff. We have to develop a bit of new stuff to get into the space, that's clear. But we really would like to get the community to move into this deeply embedded world in a sustainable way. And this goes, I mean, of course, all the companies involved also have products based on this, and that's, of course, an interest that we will use this to support our own products, right? But we really want to take the whole community there and say, hey, microcontroller development is not something that only hardware companies of the size of Bosch or so can do. This is basically something that everybody can do. And as you may know, most of the hobbyists out there already know that. Arduino has been a huge success, right? People running stuff on microcontrollers. And this is what we would like to enable the ROS world to do. And then maybe at some point in the future, we cannot only say, hey, this device supports ROS because there's a driver for it. We can say, hey, it runs micro-ROS, and it directly talks ROS messages, and it has ROS system modes, and can consume TF and all that on the device. That would be the goal. Thank you for your attention, and if there are any questions, I'm happy to help.
Thank you, Ingo. Any questions from the floor?
You mentioned that a ROS serial-like approach was considered at some point, but it didn't make it. Can you say what you meant with that specifically? What is a ROS serial approach compared to what you're doing now, then, maybe?
So in the project, in the Opera project, we had quite a bit of discussion on the hardware, on the architectural approach. And we looked at RCL and RNW, and there's a couple of architectural choices in that, which make it things like buffering or every allocation, dynamic allocation. Most things are dynamically allocated, even though there's some work on static allocation. So we were unsure whether that's going to be suitable for really tiny devices like Arduinos, like tiny Arduinos. And so we discussed that a bit. But in the end, we thought, okay, let's take the first step now. The first step is going to these intermediate devices, which basically can run, or we expect them to be able to run, RCL and RMW natively. And because that, and then we can maybe make modifications to RCL and RMW to improve those, which would be a benefit to the whole community, right? That's the argument being made. So that's why we want to do that. Does it answer your question? Sort of? What was the other part?
Well, I mean, maybe the question was more, what do you consider a serial approach?
Oh, okay. So ROS serial to me is something which doesn't have nodes. First, it basically only has one node. And has a fairly, like ROS serial doesn't have a callback queue. It just reads messages from the wire and directly passes them off to a callback. And then processes that callback and then does the next message. And so this kind of very, very simple, essentially event loop-based thing, right? That would be, for me, ROS serial. And whereas what we are trying is really putting something in there which can run on multiple threads, multiple tasks, at some point have multiple nodes on the device with efficient inter-node communication, all that stuff. Yeah. So, and I mean, maybe that's to me is totally obvious, but so the idea would be that you have a micro-ROS-based device which runs a couple of nodes, basically from the manufacturer, and then maybe you could add yourself one more node, to do what you need. And this should be enabled, and ROS serial wouldn't enable that.
Any further questions? Otherwise, I have one concluding. You mentioned an excellent 15 out of 15 rating. What do you think was the captivating trait for the reviewers to give you such a score? Because as you said, it's not like we're doing something completely new, completely different. We're more empowering other companies, other organizations, even when they don't have the resources of Bosch to be in the embedded space. So was this, did they got this message? Or?
Well, of course we don't really know because, as you know, European Union review comments are very superficial. But what I think is at least partially behind it is that we made a case in a proposal that this would leverage European strengths, where Europe has a very good deeply embedded community. We have a couple of good microcontroller manufacturers here, STM, for example, and lots of existing other domains are using microcontrollers in domestic products and in various things. So we thought we had a good strength here that we could leverage to maybe take a bit from the US dominance of the ROS ecosystem so far and get a little bit more strength into Europe. Well, that's a political story, right? And I don't really want to put them versus us kind of thing, but I think for the reviewers that was certainly a bonus. And it's true. I believe that we have a good strength in this space and a lot of competencies and a lot of talent, and that we can leverage this.
Thank you again, Ingo.
Okay.